Hi everybody, got a new puzzle here. It's called XY Differences 5 Knapp daneben, which in German means close miss, near miss. So it's an XY differences puzzle, except the keys are one off. So for me to explain this, it's a little bit wordy here, so I'll show you what that means. Now this is the first XY differences puzzle I've done, so I didn't know how this worked before either, but here it goes. The first cells in each column are essentially the key for that column, as are the first cells in each row are the key for that row. And the key defines the differences between cells separated by diamonds on that row or column. Now what that means is, for example, if this cell here is a 2, then the difference between these two must be a 2. And if the cell up here is 3, then the difference between these is 3, between these is 3, these and these are all 3 exactly. Now that's a normal XY differences puzzle. This is a near miss XY differences puzzle, which means, for example, if the number 3 was here, then these are separated by 2 or 4. These are separated by 2 or 4, as are these and these and these and so on. If this was a 5, then these are separated by 6 or 4, 6 or 4, 6 or 4, and so on. So the rules might look like they're not giving us much information, especially with the near miss constraint, but there's actually some cool stuff we can do with it. So let's get started. Much of this puzzle has to do with parities. Now, the parity of a number is whether it's even or odd. Now, we are going to do a lot of work in this puzzle where we decide the parity of a cell before we know anything else about its value. So I'm going to use a standard where I mark even cells as blue and I mark odd cells as yellow. I'm going to use these colors to record the parity of a cell. So we're going to use a property of the parities of addition here. And that property says that if you have a number and you add an even number, then the result is the same parity. And if you have a number and you add an odd number, then the result is a different parity. So, for example, if we know the difference between these two is even, then we know they are the same parity. And if we know the difference between these two is odd, then we know they're different parities. Now, the reason that's relevant to XY differences is that once we know the parities of the key values in the first cells in a row and column, that will tell us the differences between all of the other cells in that row or column that are separated by diamonds. Now, in normal XY differences, if this is even, then the differences are all even. But because this is a near miss and it's always one greater or less than, we know that if this is even, then the difference between all these cells is odd. Because if you add or subtract 1, you're changing the parity as well. So for example, if this here is even, then we know the difference between these two is odd, which means an even plus an odd is odd. And then the difference between these two is odd again. So if you take an odd and you add another odd, you get to even. So if we knew that this was even, we would know that this is odd and then that's even, and so on. Similarly, if we knew that this here was odd, then we'd know the difference between these two is even, and that would mean that this is also odd. And the difference between these two is even, then that would also be odd, and that would also be odd, and that would also be odd, and odd, and odd, and odd, all the way down. And in fact, this here is the first thing we're going to do to solve this problem. If this here was odd, then these would all need to be odd, and there are certainly not 8 odd numbers less than 9. So let's remove all the notations we have, and we can start our solve by saying that this up here must be even. Now, before we go too far, there's another rule I want to show you. Now, all sequences are either alternating parity or they're a consistent parity. So for example, if this is odd, we know these are all odd. And if this is even, we know every second one is even. Now, what's consistent between those two things is in a continuing sequence, every second parity is exactly the same, because our only options are continuing the same, which will make them the same, or alternating, which will make them the same. So any place where we have a parity and then we have a gap of 2 with 2 diamonds, we can say that that third one is also the same parity. So I'll remove those examples, but in here, this being even means that this is even, and this is even. Now, of course, we already have our 4 evens for this row, and we can fill in the rest being odd. So now let's start looking at these two long sequences in row 2. Now I want to decide the parity of this cell here. If this was even, then we know we would have alternating parity on this row, which would make this even and that even. So we already have 3 evens. Now, this sequence of 4 also needs to be alternating. So no matter how this goes, we're going to have 2 more evens in here, giving us a total of 5 evens in a row, which is, of course, impossible. So that first cell must be odd, meaning all of these are odd, because an odd key means an even difference, which means continuing parities. And then we need to fit our 4 evens in here. Now let's start taking a look at column 2. Our two-way rule says that this must be even as this is even. Now this being even means we're alternating in parities between diamonds on this column. So this one must be even. Now this guy being odd places this guy odd because it's 2 away, which makes this guy even. And another two-way rule we have is from here, this odd places an odd here also. Now we have quite a tricky thing happening in box 2. Notice that we already have 3 of our 4 evens placed, and 2 of these are on diamonds. Now, if one of these diamonds was a repeating parity sequence, that would be okay. It would place our 4th even up here. But if they were both repeating sequences, then we would end up with 5 evens in this box, which is impossible. So what that means is these can't both be repeating sequences. And a repeating sequence is given by an odd key. Now, these two can't both be odd. Fair enough, but they must be the same. So since they must be the same and they can't both be odd, they must both be even. Now we've placed 2 more evens and we've got to 4 evens in this box, so we can fill that out, the rest of that with odds. Also, if you take a look in this column, we have 2 evens here, and we know since these are alternating, there's going to be 1 even in this and 1 even in this. So the final one must be odd for us to finally get 5 odds. Now, given that this is even, we know these are changing, so we can place odd and odd here. Now look at this. This is odd, so these are consistent. So we go blue copies blue here, and this is odd, so these are consistent. Blue copies blue here. We've got these 3 nice little evens in here. And row 3 being even, meaning we have alternating parities, we already have 3 evens, and these are alternating, so one of them must be blue. Now, one of these being blue means in row 3, we now have all of the blues set, and in this box, we have all of the blues set. So we have to go yellow, 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 yellow. Now, the final place in row 1 and in box 2 for the final even is here. Now let's do some coloring of parities that are different but not known, which is these. If we look at this sequence of 3, they must be the same because this is yellow. If we look at same with this sequence of 3, they must also be all the same. And these 3, given that we have a yellow here and a yellow here, these must all be the same. So we know these are the same parity, I'm going to call it pink. And we know that these can't be the same parity, because then we would have 6 of the same parity in one box, and that's not possible. So I'm going to call those green. And for the same reason, these must be green. They must be the same, but they can't be the same as pink. So we've colored these knowing that they're different sets of parities, but we don't actually know what parities they are, just that they're different to each other. Now let's look at these 2 here. Because this is odd, these must be the same parity. Now can they both be even? Or can they both be odd? If they were both odd, we would need 4 evens in all of this. And we can only have at most 1 even here. So to say again, if these were both odd, we would need 4 evens in all of this. But this can only be 1, which means these 3 must be even, because we'd only get 1 here and the other 3 from here. Now, if these 3 are the same, then we've got all of this the same, and even or not, we can't have 6 of the same parity. So all of that is to say, these can't both be odd. At least one of them must be even. But because this is yellow, these must be the same. So these are both even. Now in column 2, we have all 4 evens set, so the rest of that column must be odd. Now that's all we can do for now with just parities, or at least all that I could find. So let's actually start using the values of these cells. So I'm selecting all the blues, and I'm saying these must be 2, 4, 6, and 8. And now I'll select all of the yellows, and I'll say these cannot be 2, 4, 6, and 8. So now we have a candidate representation of the odds and evens as well. Now we need to start getting into some details of digit sequences. A simple one is 8. If this is 8 or this, um, think about what this sequence can look like. If this is an 8, difference can never be 9. There is no one, the largest difference possible is 8, which is 1 to 9. So the difference can never be 9. If the difference is 7 and we start here with 8, we can only go 8 and then down by 7 to 1. We can't then go up by 7 to 8 again. So if the key is 8, we have very limited options, and we certainly can't have a long sequence like that. Similarly here, we can't go 8, 1, 8, we can't go 8, 1, 8. So I can take 8 out of this, and this, because none of those are actually possible. So 8's got to sit over here. Now if we look at the 8's in box 1, it can only be one of these two options. Now let's think, can this be an 8? We have a sequence of 3 here. Now, is it possible to have a sequence of 3 with 8? It's not at all. We can't go 1, 7. The issue is that we can only ever move by 7, which means we can only ever move monotonically, which means the longest possible sequence is 2. So if 8 is the key, the longest sequence is 2. This can't be an 8 either. So that makes this an 8. So now let's think about 6 in a similar way. We have 6's potentially being all 3 of these, and we have sequences of length 8 and of length 3 and of length 4. Now let's think about what a sequence starting with 6 and keyed by 6 will look like. So if we're dealing with 6, the difference is going to be either 5 or 7. So we're starting with 6. Now, can we go up or down by 7? Absolutely not. So we have to go down to 1. And from there, we can't go up by 5 again to 6. So we're going to have to go up by 7 to 8. And from 8, we can't go up. We're going to have to go down. And then we can't go down by 7. We're going to have to go down by 5 to 3. Now from 3, again, we can't go up by 5 again. So we're going to have to try to go up by 7, which we can't do. So the only possible sequence keyed by 6 and starting with 6 is 6, 1, 8, 3 exactly. And at most, we could have just 6, 1 if there was only 2 diamonds, but if there's enough diamonds, we're going to get to 6, 1, 8, 3. Now, is that possible here? It certainly is not possible for this to go 6, 1, because we would go 6, 1, 8, 3, and then we can't continue. So that's not a 6 there, meaning one of these is a 6, so that's not a 6. Now here, we have an 8 here. So we could actually go 6, 1, 8, 3 usually, except the 8 is placed here. So we can't go 6, 1, 8, 3. We're going to have to go 6, 1, 8. Now this can't be a 3. It doesn't need to be 6, 1, 8, 3 because there's no diamond here. But this 8 here eliminated this from being a 6, 1, 8, 3. So here we are. Now let's start looking at what this sequence might look like. We have another longish sequence keyed by its start. So what about 9? With 9, the only possible difference is 8. And the only two digits that can be separated by 8 is 9 and 1. So 9 and 1 is the only sequence keyed by 9 that starts with 9. So certainly we don't have a 9 here. And by the way, that makes one of these 3 a 9. So I'm going to eliminate 9 down here. Now let's think about 7. 7 means a difference of 6 or 8. So if we start with 7, we're certainly not going up, and we're certainly not going down by 8, so we're going to go to 1 immediately. After that, we can't go up by 6, we'll have to go up by 8 to 9. Then we can't go down by 8, we'll have to go down by 6 to 3. Now, we can't go down at all, and we can't go up by 6. We're going to have to go up by 8, but that gets to 12. And look, we can't have 7, 1, 9, 3, because we have another diamond here. This would need to be a very large number. This would need to be 11 or something. So this can't be 7. All right, we're not going to place a 7 there. And again, look, one of these has to be 7, so I'm going to eliminate 7 all the way down here. Now, the reason we looked at that is we actually care about this cell here. Now, there's something interesting we're going to see and use a little bit later on where notice this 3 and 5 is just separated by 1. If this was a 4, then the gap here would be 1, whether this was 3 or 5. Um, so this can only be 4 if a 1 is an allowed gap in this sequence. And if this is a 4, obviously 3 and 5 are the only allowed gaps. So if this was a 4, 3 and 5 would both be impossible, which means this must be a 2. That gives us a 4 over here and a 4 down here. And this 2 is quite nice. It's told us a lot about this row and about this column, so the gap can only be 1 or 3. So both of these values are still okay. But from a 4, can we get to all of these from 1 or 3? Most of them. We can't get to a 9. So that can't be a 9. Now we think along these terms. 6 can get to all of these values, but 4 can't get to all of these values. 4 can't get to 9. So this can't be a 9 because it couldn't have a diamond between that 9 and a 4. So I'm going to remove that 9. Now if we think about 3 and 5, the largest possible gap, whether this is 3 or 5, if this is 5, the gap would be 6. Which means if this was 1, the maximum this is 7. So this can't be a 9 either. So that can't be a 9, and we've placed our 9. In box 1, the 9 can only be here. Now, in this row, the key is 4, so the gap is either 3 or 5. And if this was a 2, this diamond would be invalid. So this can't be a 2. We must place a 6 here, which means we're going to now be placing a 2 up here. Now, once we've placed this 6, with a gap of 4, we can't go 5 or 7. If this is 5 or 7, the gap is only 1. So this is not 5 or 7 here. Now let's start looking at column 4 here. Now, this being a 4, and also this being a 6, let's remember that the difference here has to be 3 or 5, so we're never going to have gaps of 1 allowed. So 3 and 5 is not possible here. But also, because this is a 6, if this was a 7, the gap would be 1, which is not allowed. So this must be a 9. Now again, because we are not allowed gaps of 1, this cannot be 5 or 7. Now this one here can't be 2, because whether this is 1 or 3, the gap will only be 1. This certainly isn't 2, which makes it 8, which makes 1 infeasible now, because we can't have a gap of 7, so that there is 3. This 8 gave us a 2 for free down here, because we already had 4 and 6 eliminated, so we can place a 2 here. The 8 eliminates this 7, and this 2 eliminates this 1, so this must be a 5. Now from this 2, we can't make a 1 gap to 1, so it has to be a 5 gap to 7. So that's a 7, and that's a 1. Now that's quite nice. We've set this entire row. Now while I'm at it, this gap here is 6. So the possible gaps here disallow 3. Certainly this can't be 3. Now if this was a 5, regardless of the value of this, we're screwed. So this can actually never be a 5 regardless of the value of this. With a 6 key, the differences are either 5 or 7. If we're at 5, the gap can obviously never be 7. It can also never be 5. We can't have 0 or 10. So this certainly can't be a 5. This here must be a 9. Now, we can have a gap of 7 to get to the 2, and we can have a gap of 5 to get to the 4. So these are both still okay. Now let's start thinking about the negative constraint. One of the rules in this puzzle is that all possible diamonds are given. So, if either of these cells, if we're thinking about this 8, if either of these cells are a gap of 1 or 3 away from the 2, then there would need to be a diamond there, but all possible diamonds are given. So we can't create any new situations that would require diamonds. So the values 7 and 5 are both 1 or 3 away from the 8, so we can say these are not 7 or 5. And also this 9 here is 1 away from the 8, so that's not 9. And look at that, we have a naked 1, 3. It's quite interesting. So I'm going to say these guys cannot be 1, 3. And additionally, we have a naked 1, 3 here and here, which means that these two cannot be 1 or 3. Now let's start looking at row 2. There's an interesting thing we can do here with this 5. If this here is a 5, then where can this 9 go? This 9 could not connect to a 7 because the gap would only be 2. The 9 could, you could subtract 4 from the 9 to get 5, but then we'd have 5. So if this was a 5, this would have to be a 9 and this would have to be another 5. We'd end up with two 5s here. So that makes no sense. This can't be 5. This is going to be 3. Now, from 1, we can't reach 7, so we must go to 5 here, which places a 7 here. We also get a 7 up here. We get a 5 down here. Now we can do another cute little negative constraint thing here. If we have a 3 here, the gap to that 7 would be 4, and there would need to be a diamond. So this certainly is not 3. This is a 1 here, which places a 3 here and a 3 here. Now there's another fun little thing here. We have a diamond here and a key of 4. So the gap here is either 3 or 5. But in this whole box, the only places a 2 is allowed is in these two. So one of these is a 2, and the other, well, the other can't be a 1 because then the gap would only be 1. These have to be 2 and 7 between them, meaning this is a 1 here. All right, now let's start thinking about row 8. If this here was a 5, if the key was a 5, we would necessitate a diamond here. So from the negative constraint, I can remove 5 from here. If this were a 1, then the only possible difference would be a 2. So a 9 would have to step into a 7, which clearly it can't do. This can't be a 7 because that's a 7. So this can't be a 1. Now, if this were an 8, well, let's think about what a 9 sequence that starts with 8 might look like. There's no possible gap of 9, so the difference has to be 7. So we're going to go from 9 to 2, and then from 2, we can't go up back to 9, and we can't go down, obviously, so we would get 9 2, and that would be the end of the game, but we have another diamond to think of. So this certainly can't be an 8. This here must be a 6. Now, we know the parity there. I'm going to color that. Now, what's our rules? If this is even, then the parity must be changing. So we must have an even in here. So I'm going to eliminate 1 and 3 from there. And again, it's changing because this is even up here, so this must be odd down here, which means I can eliminate 8 from that cell. Now these are even odd in some order, but we're not yet sure exactly how. Now let's take a closer look at these gaps here. With a key of 6, the gaps must be 7 or 5. Now with a 7, we can certainly not have a gap of 7. It's going to have to be a gap of 5, which means this has to go down to 2. This must be a 2 here. So we have a gap of 5 here, then a gap of 7 here. That works. And that gives us a 4 down here, which gives us a 2 up here. Now let's think about this 2 and its negative constraint with a key of 7. If either of these were an 8, the gap would be 6 and then we would require a diamond. But there's no diamond, so neither of these are 8. That tells us that this is a 3, that this is a 1, and that this is an 8 here. This is the only place that could be 8. Now I'm going to color these parities because it will look nicer that way. Now look, in this column, we have our 4 evens already. And in this box, there's only place for 2 more evens, so it must be these two. Now conveniently, these we already knew were only even digits, so our coloring is looking good, but not doing all that much for us. But look at row 5. We now have 3 confirmed evens on row 5, which means we can decide the parity of these two. If green was even, then we'd end up with at least 5 evens in row 5, which makes no sense. So green must be odd, and pink must be even. Now I'm just going to select these and set their parities. These are not 2, 4, 6, 8, and these are 2, 4, 6, 8. Beautiful. Now, after we set those parities, we have a naked 5 here. Why is that? Well, we know it's odd. We know it can't be 1 or 3 because of these. We know it can't be 7 or 9 because of these, so the only one left is 5. So I'm going to place a 5 here. So this 8 is going to tell us what this is because we have a diamond. We can't do 2 plus or minus 9, obviously, so we're going to have to do 2 plus 7 to get us to 9. So that's a 9 there, and I'm going to color it as well. So look, we have a 4, 8 and a 4, 6 up here. These must be even, which means this guy must be odd, and the only way he can be odd is with the number 5. We've also unveiled a 7 over here, so we can place a 7 here, 5 over here. We've got a whole bunch of things just appearing before our very eyes, which is quite nice. Now in this box, we already have our 4 even, so we can get rid of these. Say these are not even, not 2, 4, 6, or 8. And now in this row, we know we already have our 4 evens, so these must be odd. Now in this box, we need our 4th even, so it's going to be placed here. So let me just mark down that these are not 2, 4, 6, and 8, and this is 2, 4, 6, and 8. Now we also have a naked 7 down in the bottom left, and this key of 6 means parities are changing. So this must be odd, and the only way it can be odd is for it to be 3, which gives us a 4 up here, and we've placed some parities, and we've got an 8 here. Wonderful. Alright, this 8 can also tell us about this. The key is 2, so the gap can be 1 or 3. This certainly can't be a 1. Must place a 9 here. Now we can use negative constraints again. This 2 cannot be separated by 5 beneath it, because this is a key of 6. So if there was a gap of 5 here, there would be a diamond here. So this certainly is not 7, it must be 3. We're putting a 3 here and here, placing a 7 here, and a 1 over here. We also have a naked 6 down here now. Another negative constraint is this 1. If this was a 1, then we'd have a gap of 2 to the 3, which would require a diamond. So we can place a 5 here and a 1 there. Now, placing this 3 over here did something a little bit subtle. What's the maximum difference here? The maximum difference here, if this was a 9, would be 6. So this certainly can't be a 9, because it's impossible to have a gap of 8 here. So you can place a 5 here, and there, and a 9 here. Now this gap of 5 tells us this is not 1. This is either 7 or 6. Now the only 1 in this box is there. Placing another 1 there. 4. Now we have these naked 7, 9s. They eliminate this 7. Placing a 7 there and a 2 there, which gives us an 8 down the bottom, a 2 over here. We also have a 4 up here. And let's color all of these odds and evens. There we go. We have the parity of the entire board set. That's quite nice. Now, if this were 9, then the gap to the 1 would be 8, which is not possible with a key of 5. That's not 9. This must be 7. Giving 7 there and some 9s here and here. Now, also this 1 over here means the gap is 2 exactly. So this must be a 4 right here. Placing a 6 here, an 8. Unwinding a lot of these undecided evens around the place. I'm just following the naked and hidden values around. So this is all solved except for a little 2424. Kind of looks like a fatal rectangle or a forbidden rectangle or whatever they're called. But what actually is it? It is this. If this was 6 and 4, the gap would be 2, which would be disallowed. I'm sure there are lots of ways to solve this, but there you go. We can't have a gap of 2 here, so this must be 2. 4. Check errors. We are all good. So there we go. That was XY Differences 5. Knapp daneben by Glum Hippo. Thanks very much, dude. That was a good puzzle. Thanks, Victor, for solving this puzzle with me. I'm now working on quite a mouthful, which is a very difficult puzzle. I suspect I won't finish it, but if I do, I'll make a video of it. Anyway, thanks for watching, guys. See you later.